Hello and welcome to my virtual talk recording for the Environmental Seismology section of the Fall 2020 AGU meeting. My name is Marshall Boris. I recently graduated from Williams College, and I'll be presenting on the seismic detection of ridging and ice deformation in coastal sea ice near Utqiagvik, Alaska, or, as I like to call it, sensing stability with seismology. So a quick outline of this presentation. I'll begin with background, research goals, methods, going through data acquisition and seismic analysis, then wrapping up with the results. How do the signals look? Conclusions, what do those signals mean? So beginning with background, what are ice ridges, why do we care, and where are we looking? So our research site is in, once again, Utqiagvik, Alaska, the northernmost community, and Utqiagvik is unique because it hosts both a sea ice radar and a transportable array seismic station. We're looking at sea ice and its interactions and collisions with the shoreline, and we're doing this in the hopes of developing a new method of observing shore ice interactions using seismic data. So why sea ice? Coastal ice is important for travel and hunting in Utqiagvik communities that rely on sea ice for the local economy, subsistence, and cultural activities. The stabilizing of shorefast ice is a critical piece of this. So now let's look at ridging. Quick crash course on sea ice collisions. Early in the winter, around October, cold air temperatures cool the ocean surface to the freezing point, and it freezes through a semi-consolidated slush phase into solid sea ice. Drifting ice flows, circled in red, can be pushed towards ice frozen to shore. During these convergence events, ice at and near the boundary fractures and is pushed up and down to create a ridge, shown in the middle figure here. Through a combination of ice growth and successive ridging events, these ridges can reach down far enough to become embedded in the seafloor. Sea ice between the grounded ridge and the shore is stabilized and is referred to as shore-fast sea ice. These ridges are visible on the surface to an observer, but it's difficult to know exactly when they become grounded as it happens below the ice surface. Previous research on cryoseismology is focused on glacial calving, ice sheet stability, sea ice ocean cover as it relates to microseisms, with a general overarching theme of Arctic monitoring or remote sensing. However, nothing is focused on shore ice interactions. This leads us to our big picture goal, which was to detect and characterize ridging events by their seismic signature. I like to split this big picture goal into three smaller goals. First, these interactions have never been seismically studied, so we needed to make sure that they can actually be detectable with a seismometer. Second, we wanted to see if we could characterize these events based on specific, unique features. Third, we were interested in seeing if we could differentiate between different types of events based on these characteristics. And now onto our methods. There were 4 steps to our approach: watching radar footage to choose events, applying feature tracking to that radar footage to quantify speeds, averaging the seismic signals of events, and finally comparing power ratios of those events. Once again, the first step was event classification. We did this by watching the marine sea ice radar footage and creating a database of potentially seismically interesting events. Included below is a sample of that marine radar footage on the 3rd of March 2015. What you see happening is pack ice moving towards the shore in what we consider a convergence event. The green area is land, and the moving white pixels are sea ice. The marine sea ice radar and transportable array seismic station overlapped for 2 ice seasons. We began by watching the radar footage for each day and creating a database of what the local sea state was on that day, and finally, if it was seismically interesting or not. We had a good qualitative measure of what was happening, but we still wanted more quantitative metrics, such as speed and direction. As a result, we applied feature tracking to the radar footage, and these are the blue arrows overlaid on the radar. While we were hoping to use the feature tracking to automate the detection of events, which is what I presented on last year, due to the dynamics of the sea ice not aligning with the moment of greatest impact, the human eye tended to be a bit more efficient at selecting events. We were looking to create a data set with 3 distinct groups: ridging events, where ice was moving towards shore and we saw deformation, such as the previous radar footage; breakout events, where formerly stable ice broke off from shore; and high wind days, which we expected to be particularly noisy. In total, we had 70 unique events. Once we had our event times, we would request that window of seismic data from IRIS. In this case, 3 a.m. on the 2nd of March until 3 a.m. on the 3rd of March, the day of the ridging event I showed previously. We would smooth, demean, and downscale the data before performing a fast Fourier transform to get the data into frequency space. At this point, you have the plot on the right here. This being an environmental seismology section, most of you are familiar with spectrograms, but for those of you who might be coming from the cryosphere, the way to read this plot is that on the x-axis you have time, and on the y-axis you are moving up the frequency range. On the color scale, you have lower power in blue and higher power in tan in red. We would then take these frequency domain signals and average them across each frequency bin. The last step was to compare the signals. We did this using a form of primary component analysis, using the ratio of 2 power bands. We wanted to use the ratio of powers to block any difference in normalization procedure. In the end, we wanted to find 4 frequency bins, creating the most distinct clustering. To do so, we ran k-means clustering on all 33 to the 4 combinations, and calculated the false positive and false negative rates. K-means clustering partitions our 70 observations into k clusters, in this case where k is equal to 3, to account for 3 event types, ridging, breakout, and high wind. It forms these groups by minimizing within cluster variance, or in other words, the mean distance for each observation to the centroid. To nail this down one more time, we wanted to see which 4 power bands created the most distinct grouping. We wanted to see all the ridging events grouped together, the breakout events grouped together, and lastly, the high wind days paired together. Those were our methods. Now onto the results. What do the signals actually look like? To circle back to our initial question once more, we wanted to 1. Be able to detect these events, 2. Be able to characterize them, and 3. Be able to differentiate between them. So first, detection. As you may have been cheeky enough to guess by now, this was a strong validation. Yes, we can detect ice-shore interactions via seismic signals. There's both a clear spike in power and a clear delineation of when events begin and end. Second, we wanted to characterize these events. We originally had wanted to create an averaged frequency profile for the 3 different events and background noise levels. Ridging is here in yellow, breakout is in red, high wind days are in blue, and lastly, we have 2 background noise signals, early winter season in purple, late winter season in green. So what these are, these last 2 signals, are 300 randomly sampled events for, in purple's case, the first half of the ice season, and in the green signal's case, the second half of the ice season. So what can this tell us? Well, there's certainly a lot here, but it wasn't exactly conclusive for what we wanted to see. We could see that the 3 different types of events were unique and showed different patterns at different areas in the frequency spectrum. But all we could really do at this point was do some hand waving and point to general trends. That's what led us to our power ratio comparison. Unlike what we saw with feature tracking, the computer beat the human this time. So what we have on the screen now is the grouping of the 70 test events along with 600 randomly sampled events based on the 2 most optimal power ratios. Once again, we got these power ratios from the k-means clustering. The red and yellow dots here are confirmed or suspected ridging events from our event classification. The blue are confirmed non-ridging events, also from our event classification. Note the clear grouping and separation of the ridging events. The 2 ridging events that are mixed with the non-ridging events, i.e. false negatives, are a result of very early season thin ice and very late season ice with large melt pond coverage, both indicative of structurally weak ice. So this touched on our goal of 1. Being able to find characteristic frequencies for these signals, and 2. Being able to differentiate between types of events. Lastly, we also hope to be able to differentiate between grounded and ungrounded sea ice signals. When you look at the background signals from early in the season, when you expect ungrounded ice, once again in purple here, and compare it to the background signal for late in the season, when ice would be grounded, we see an inverting of power across the entire spectrum. There's an inflection point around 1 Hz, but across the entire frequency spectrum, the 2 signals do not track each other. So finally, conclusions. What does this tell us? First, ice ridging creates detectable seismic signals in specific frequency ranges with a clear signal duration. Second, we were able to differentiate ridging events from other potentially noisy days, breakout events, high wind, and background noise levels. We were able to do this by comparing the power bands at 4 specific frequencies, and to do so with remarkably low, false negative, and false positive rates. Third, we saw that there was a background difference between grounded and ungrounded ridges. To quickly touch on potential future work or expansions for this project. This project used backwards-looking data in the hopes to create a model to run on real-time data. So first and foremost, the next logical step would be to go to real-time detection. To do this, we would need to work with community members to learn what performance indicators could be useful and to have community deployment. Lastly, more sensors, more data, and a possible network of low-cost seismic sensors along the coast to monitor coastal sea ice. So with that, I conclude my presentation. I'd like to thank Alice Bradley, my advisor on this project, for contributions, mentorship, and crazy MATLAB skills. I'd also like to thank Casey Adderhold at IRIS for her help with the seismic data and being the residential seismic expert. Thanks for viewing my presentation, and I look forward to answering questions on December 9th.